The universe is vast, mysterious, and filled with wonders that defy explanation. Picture this, a signal from deep space, so powerful and precise, it was detected only once and never again. Or imagine a star that dims and brightens in ways that no natural phenomenon can explain. These are not scenes from a science fiction movie. They are real, unsolved mysteries that continue to baffle scientists around the world. Welcome to a journey through the top 30 astronomical phenomena still unexplained by science. Despite centuries of exploration and discovery, the cosmos holds secrets that challenge our understanding of reality. From invisible forces shaping galaxies to strange objects hurtling through space, the universe reminds us that there is still so much we do not know. So, buckle up and prepare to explore the unknown as we dive into the most perplexing mysteries that keep astronomers awake at night. By the end of this video, you'll not only marvel at the wonders of the cosmos, but also gain a deeper appreciation for the questions that remain unanswered. Let's begin. Now turning to one of the most intriguing mysteries in the history of astronomy, we encounter the WOW signal. In the summer of 1977, the Big Ear radio telescope at Ohio State University picked up a signal so unusual that it left astronomers stunned. Lasting for 72 seconds, the signal was so strong and precise that the astronomer who discovered it, Jerry Amon, circled it on the printout and wrote, "Wow." Next to it, a name that has stuck ever since. The signal appeared to originate from the direction of the constellation Sagittarius, and its frequency matched the expected range for transmissions from extraterrestrial sources. Yet, despite numerous attempts to detect it again, the WOW signal has never been heard since. Theories about its origin range from a natural cosmic event, like a comet or a distant star, to the tantalizing possibility of an intentional transmission from an intelligent civilization. However, none of these explanations fully account for its unique characteristics or its sudden disappearance. The WOW signal remains a tantalizing enigma, a fleeting whisper from the cosmos that continues to spark curiosity and debate among scientists and enthusiasts alike. What could it have been, and why has it never been repeated? These questions linger, reminding us that even in our search for answers, the universe often leaves us with more mysteries than solutions. Now shifting our gaze to another profound cosmic mystery, we delve into the enigmatic realm of dark matter. This invisible substance is believed to make up roughly 85% of all matter in the universe, yet it remains completely undetectable by conventional means. Unlike stars, planets, or even gas clouds, dark matter does not emit, absorb, or reflect light, making it invisible to telescopes. So how do we know it exists? The answer lies in its gravitational effects. Astronomers first began to suspect the presence of dark matter when they observed that galaxies were rotating far faster than they should based on the visible matter alone. Without some unseen mass providing additional gravitational pull, these galaxies would simply fly apart. Similarly, the bending of light from distant objects, known as gravitational lensing, also points to the presence of massive, invisible structures in space. Despite decades of research, dark matter's true nature remains one of the greatest unsolved puzzles in modern science. Is it made up of exotic particles that interact only weakly with ordinary matter? Could it be a sign of new physics beyond our current understanding, or is it something even more mysterious, defying our current frameworks entirely? While experiments like those conducted in underground labs or with particle colliders aim to uncover its secrets, dark matter continues to elude us, a shadowy presence that shapes the cosmos yet refuses to reveal itself. As we grapple with this invisible giant, we're reminded that the universe is far stranger and more complex than we can imagine, and that some of its deepest secrets may still lie just beyond our reach. Now turning to another cosmic enigma, we encounter dark energy, a mysterious force that is reshaping our understanding of the universe. Unlike dark matter, which pulls galaxies together through gravity, dark energy is pushing the cosmos apart at an ever-increasing rate. This discovery, made in the late 1990s, came as a shock to scientists. By observing distant supernova, astronomers found that the universe's expansion was not slowing down as expected but accelerating. This unexpected behavior suggested the presence of an unknown energy permeating space, now called dark energy. But what exactly is it? Current theories suggest that dark energy could be a property of space itself, often referred to as the cosmological constant, a concept first proposed by Albert Einstein. Alternatively, it might be a dynamic field that changes over time, known as quintessence. Yet, despite decades of research, its true nature remains elusive. One of the biggest challenges is that dark energy doesn't interact with light or matter in any detectable way, making it nearly impossible to observe directly. Scientists rely on indirect methods, such as measuring the large-scale structure of the universe or studying the cosmic microwave background, to infer its effects. The implications of dark energy are profound. If it continues to dominate the universe, it could lead to a future where galaxies drift so far apart that they become invisible to one another, leaving the cosmos cold and empty. As we grapple with this invisible force, we're reminded that the universe is full of surprises, and that some of its most fundamental questions are still waiting to be answered. With every new observation and experiment, we inch closer to unraveling the mystery of dark energy, but for now, it remains one of the most tantalizing puzzles in modern cosmology. Now shifting our gaze to another cosmic mystery, we delve into the enigmatic world of fast radio bursts, or FRB. These are incredibly brief but powerful bursts of radio waves that last just milliseconds, yet they release as much energy as the sun does in an entire day. First discovered in 2007, FRBs have since captivated astronomers with their unpredictable nature and immense power. What makes them even more intriguing is that they originate from deep space, far beyond our galaxy, yet their exact sources remain a puzzle. One leading theory suggests that FRBs could be linked to highly magnetized neutron stars known as magnetars. These dense stellar remnants, born from the explosive deaths of massive stars, possess magnetic fields trillions of times stronger than Earth. When these magnetars experience starquakes or magnetic eruptions, they might release the intense bursts of energy we detect as FRBs. However, not all FRBs fit neatly into this explanation. Some repeat sporadically, while others are one-off events, adding layers of complexity to the mystery. Another tantalizing possibility is that FRBs could be signals from advanced extraterrestrial civilizations. While this idea sparks the imagination, scientists approach it with caution, emphasizing the need for more evidence before jumping to such conclusions. The challenge lies in the fleeting nature of these bursts. By the time telescopes detect them, they're already gone, leaving behind only a faint trace of their existence. To complicate matters further, FRBs often travel through vast cosmic distances, interacting with the intergalactic medium along the way. This interaction distorts the signals, making it even harder to pinpoint their origins. Despite these challenges, astronomers have made significant strides in recent years. For instance, some repeating FRBs have been traced back to their host galaxies, offering clues about the environments where they originate. Yet, the fundamental question remains: what cosmic processes or objects are capable of producing such extraordinary bursts of energy? As we continue to study these fleeting signals, FRBs remind us of how much we still have to learn about the universe. They challenge our understanding of astrophysics and push the boundaries of our technological capabilities. With every new detection, we edge closer to unraveling their secrets, but for now, fast radio bursts remain one of the most captivating and unexplained phenomena in the cosmos. Now turning our attention to another cosmic enigma, we explore the peculiar case of Tabby's star, officially known as KIC 8462852. This star, located approximately 1,400 light-years away in the constellation Cygnus, has baffled astronomers with its erratic and unpredictable dimming patterns. Unlike most stars which dim in regular, predictable cycles, Tabby's star experiences sudden and dramatic drops in brightness, sometimes by as much as 22%, leaving scientists scratching their heads. One of the most intriguing theories proposed to explain these unusual dimming events involves the possibility of alien megastructures. Some researchers have speculated that a massive, artificial construct, such as a Dyson sphere, could be orbiting the star, periodically blocking its light. A Dyson sphere is a hypothetical structure that advanced civilizations might build to harness the energy of a star. While this idea captures the imagination, it remains highly speculative, and scientists emphasize the need for more concrete evidence before considering such extraordinary explanations. On the other hand, natural phenomena offer more grounded possibilities. One leading theory suggests that the dimming could be caused by massive clouds of dust and debris orbiting the star. These clouds could be remnants of a planetary collision or the remnants of a disintegrating comet swarm. Such events would create irregular patterns of dimming as the debris passes in front of the star from our vantage point. Observations have shown that the star's light dims more in certain wavelengths, which aligns with the idea of dust particles scattering and absorbing light. Another possibility is that Tabby's star is surrounded by a swarm of large, irregularly shaped objects, such as fragments of a shattered planet or a dense ring system. These objects could intermittently block the star's light, causing the observed dips in brightness. Additionally, some scientists have proposed that the star itself might be undergoing internal changes, such as fluctuations in its magnetic field or unusual stellar activity, though these explanations struggle to account for the extreme and irregular nature of the dimming. Despite years of observation and analysis, Tabby's star continues to defy easy explanation. Its behavior challenges our understanding of stellar physics and the dynamics of planetary systems. Each new observation brings us closer to unraveling the mystery, but for now, Tabby's star remains a captivating puzzle, reminding us of the vast and often unpredictable nature of the cosmos. As we continue to study this enigmatic star, it serves as a testament to the enduring allure of the unknown and the boundless curiosity that drives our exploration of the universe. Now shifting our gaze to another cosmic mystery, we delve into the enigmatic force known as the Great Attractor. This colossal gravitational anomaly, located approximately 250 million light-years away, exerts an immense pull on galaxies, including our own Milky Way. Despite its profound influence, the Great Attractor remains shrouded in mystery, largely due to its position behind a region of space called the Zone of Avoidance. The Zone of Avoidance is an area of the sky obscured by the dense dust and stars of the Milky Way's galactic plane. This makes it incredibly challenging for astronomers to observe objects lying directly behind it, including the Great Attractor. Imagine trying to peer through a thick fog. Only in this case, the fog is made up of countless stars, gas, and dust, blocking our view of what lies beyond. This obstruction has left scientists with limited data, forcing them to rely on indirect methods to study this gravitational powerhouse. What we do know is that the Great Attractor is pulling galaxies, including our own, toward it at astonishing speeds. The Milky Way, along with the local group of galaxies, is moving at over 600 kilometers per second in the direction of this mysterious force. But what exactly is the Great Attractor? Some theories suggest it could be a massive concentration of dark matter, while others propose it might be a supercluster of galaxies, a dense region where thousands of galaxies are gravitationally bound together. One of the most intriguing aspects of the Great Attractor is its relationship with an even larger structure called the Shapley supercluster, located beyond it. Some scientists believe that the Shapley supercluster might be amplifying the gravitational pull of the Great Attractor, creating a cosmic tug of war that shapes the motion of galaxies on an unimaginable scale. Yet, without a clear view of the Great Attractor itself, these theories remain speculative. Efforts to study this phenomenon have relied on observations in wavelengths of light that can penetrate the zone of avoidance, such as infrared and radio waves. These observations have revealed hints of massive galaxy clusters and other structures hidden behind the Milky Way's disk, but the full picture remains elusive. The Great Attractor continues to challenge our understanding of the universe's large-scale structure, reminding us that even the most fundamental forces shaping our cosmos are still not fully understood. As we ponder the mysteries of the Great Attractor, it serves as a humbling reminder of how much we have yet to discover. Its hidden nature underscores the vastness of the universe and the limitations of our current technology. Yet, it also fuels our curiosity, driving us to develop new tools and techniques to peer beyond the veil of the zone of avoidance and uncover the secrets of this gravitational giant. Now turning to one of the most thought-provoking questions in astronomy, we encounter the Fermi Paradox. Named after physicist Enrico Fermi, this paradox highlights a striking contradiction. The universe is unimaginably vast with billions of stars and planets, making the existence of extraterrestrial life seem almost inevitable. Yet, despite decades of searching, we have found no definitive evidence of intelligent life beyond Earth. This puzzling absence raises profound questions about our place in the cosmos. The core of the Fermi Paradox lies in the sheer scale of the universe. With an estimated 100 billion galaxies, each containing hundreds of billions of stars, the odds of life emerging elsewhere seem overwhelmingly high. Many of these stars host planets within their habitable zones, where conditions could support liquid water and potentially life as we know it. So, where is everyone? Why haven't we detected any signals, artifacts, or signs of advanced civilizations? One compelling explanation is the concept of the Great Filter. This theory suggests that there is some critical barrier, a filter, that prevents life from advancing to the point of interstellar communication or exploration. This filter could occur at any stage, from the emergence of simple life to the development of advanced technology. If the Great Filter lies in our past, it might mean that the emergence of intelligent life is extraordinarily rare and we are among the lucky few. However, if the filter lies ahead of us, it could imply that advanced civilizations inevitably face extinction before they can make contact with others. This unsettling possibility raises questions about humanity's future and the challenges we may yet encounter. Another explanation is the rarity of intelligent life itself. While microbial life might be common, the leap to complex, intelligent beings capable of creating technology could be exceptionally rare. Factors such as the stability of planetary environments, the frequency of catastrophic events, or the unique evolutionary paths required for intelligence might limit the emergence of civilizations like ours. In this scenario, we might truly be alone, or at least isolated by vast distances and time. Some scientists also propose that advanced civilizations might exist but are simply too far away or too different for us to detect. They might communicate in ways we cannot yet comprehend or choose to remain hidden, avoiding contact with less advanced species. Alternatively, they might have already come and gone, leaving behind no trace of their existence. The universe is billions of years old, and civilizations could rise and fall in the blink of a cosmic eye, leaving us to search for echoes of their presence. The Fermi Paradox challenges us to rethink our assumptions about life, intelligence, and the universe itself. It reminds us that the absence of evidence is not evidence of absence, and that our search for answers is still in its infancy. As we continue to explore the cosmos with ever more advanced tools, from radio telescopes to space probes, we may one day uncover clues that shed light on this profound mystery. Until then, the Fermi Paradox stands as a humbling reminder of how much we have yet to learn about the universe and our place within it. Now shifting our gaze to a visitor from beyond our solar system, we encounter the enigmatic Oumuamua. Discovered in October 2017, this interstellar object became the first known visitor from another star system to pass through our cosmic neighborhood. Its name, Oumuamua, means scout or messenger from afar in Hawaiian, a fitting title for an object that has sparked both fascination and debate among scientists and enthusiasts alike. What makes Oumuamua so intriguing is its unusual characteristics. Unlike typical asteroids or comets, it has an elongated, cigar-like shape, estimated to be about 10 times longer than it is wide. This peculiar form is unlike anything we've observed in our solar system, raising questions about its origins and composition. Adding to the mystery, Oumuamua exhibited unexpected acceleration as it traveled through space. While comets often accelerate due to the outgassing of material as they heat up, Oumuamua showed no visible signs of a coma or tail, leaving scientists puzzled about the source of its movement. This unusual behavior has led to a range of theories about Oumuamua's true nature. Some researchers propose that it could be a fragment of a larger object, perhaps shattered by a collision or tidal forces near its parent star. Others suggest it might be a type of hydrogen iceberg, composed of solid hydrogen that sublimates in the warmth of the sun, explaining its acceleration without visible outgassing. However, these explanations remain speculative, as Oumuamua's brief visit provided limited data for analysis. Perhaps the most tantalizing theory is that Oumuamua could be an artificial object, possibly an alien probe or spacecraft. Its unusual shape and acceleration have led some to speculate that it might be a light sail, propelled by the pressure of sunlight or another advanced technology. While this idea captures the imagination, most scientists caution that extraordinary claims require extraordinary evidence, and natural explanations are still more plausible. Nevertheless, the possibility of an interstellar artifact continues to fuel curiosity and debate. Oumuamua's fleeting passage through our solar system left us with more questions than answers. Its origins, composition, and behavior challenge our understanding of interstellar objects and the processes that shape them. As we continue to scan the skies for similar visitors, Oumuamua serves as a reminder of the vast and mysterious nature of the cosmos. It invites us to keep exploring, questioning, and imagining the possibilities that lie beyond our solar system. And with that, we turn our attention to another cosmic mystery, one that involves the unexpected behavior of spacecraft in the depths of space. Now turning to a mystery closer to home, we delve into the Pioneer Anomaly, a puzzling behavior observed in two of humanity's most iconic spacecraft, Pioneer 10 and Pioneer 11. Launched in the early 1970s, these spacecraft were designed to explore the outer reaches of our solar system, providing invaluable data about Jupiter, Saturn, and beyond. However, as they ventured farther from the Sun, scientists noticed something strange. Both spacecraft were slowing down more than expected, defying the predictions of Newtonian physics. This unexpected deceleration, though small, was consistent and could not be explained by known forces like gravity or solar radiation pressure. The anomaly became a source of fascination and frustration for researchers, as it seemed to hint at a gap in our understanding of the fundamental laws governing motion in space. One of the leading explanations proposed was thermal radiation. The spacecraft's radioisotope thermoelectric generators, which provided power, emitted heat unevenly. This heat radiating from the spacecraft surfaces could have created a tiny but measurable force, nudging the probes off their predicted trajectories. While this theory seemed plausible, detailed calculations revealed that thermal radiation alone couldn't fully account for the observed deceleration. This discrepancy led some scientists to consider more radical possibilities, including the existence of new physics, Could the Pioneer Anomaly be evidence of an unknown force or a modification to our understanding of gravity? Some researchers speculated that it might be linked to dark matter or even a subtle flaw in Einstein's theory of general relativity. However, these ideas remain speculative as no definitive evidence has been found to support them. Over time, as more data was collected from other spacecraft, the anomaly seemed to fade, leaving scientists to wonder whether it was a unique quirk of the Pioneer missions or a sign of something deeper. The Pioneer Anomaly serves as a reminder that even in the well-studied realm of our solar system, mysteries persist. It challenges us to question our assumptions and refine our models of the universe. While the anomaly may never be fully resolved, it underscores the importance of precision in space exploration and the need to remain open to the unexpected. As we continue to send probes into the depths of space, the lessons learned from Pioneer 10 and 11 will guide us, ensuring that we are prepared to confront the unknown. And with that, we set our sights on another cosmic puzzle, one that lies hidden in the icy reaches of the Kuiper belt. Now shifting our gaze to the icy fringes of our solar system, we encounter another cosmic enigma, the Kuiper belt's missing mass. This vast region, stretching beyond Neptune, is home to countless icy bodies, including dwarf planets like Pluto. But here's the puzzle. The total mass of the Kuiper belt is far less than what scientists expected based on models of how the solar system formed. According to these models, the Kuiper belt should contain significantly more material, but observations reveal a surprising shortfall. So, where did all that mass go? One leading theory suggests that the missing mass might be tied to the early days of our solar system during a period of intense planetary migration. As the giant planets Jupiter, Saturn, Uranus, and Neptune shifted their orbits, their gravitational influence could have scattered much of the Kuiper belt's material outward, flinging it into the distant reaches of space or even ejecting it entirely from the solar system. This chaotic reshuffling might explain why the Kuiper belt appears so much lighter than predicted. Another intriguing possibility is that the missing mass isn't missing at all, it's just hiding. Some scientists propose that the Kuiper belt could contain a population of unseen objects, perhaps too small or too dark to detect with current technology. These hidden bodies, if they exist, might account for the discrepancy, but finding them would require more advanced telescopes and surveys. There's also the tantalizing idea that the Kuiper belt's missing mass could be linked to the hypothetical planet 9, a massive object thought to orbit far beyond Neptune. If such a planet exists, its gravitational pull could have disrupted the Kuiper belt, redistributing its material in ways we're only beginning to understand. However, the search for Planet 9 remains ongoing, and its existence is still unconfirmed. The mystery of the Kuiper belt's missing mass challenges our understanding of the solar system's formation and evolution. It reminds us that even in our own cosmic backyard, there are still unanswered questions waiting to be explored. As we continue to study this distant region, each discovery brings us closer to unraveling the secrets of our solar system's past. And with that, we turn our attention to another celestial puzzle, one that lies much closer to home, the Moon's mysterious magnetic field. Now turning to a mystery much closer to home, we find ourselves gazing at Earth's closest celestial neighbor, the Moon. While it may seem like a quiet, unchanging companion in our night sky, the Moon holds a fascinating secret in its past, a magnetic field. Yes, the Moon once had a magnetic field, much like Earth's, but today it's gone. So what happened? Let's dive into this lunar enigma. Billions of years ago, the Moon's magnetic field was surprisingly strong, perhaps even comparable to Earth's at the time. This magnetic field would have shielded the lunar surface from harmful solar radiation, creating a very different environment than the barren, airless world we see today. But around 1 billion years ago, this magnetic field vanished. The question is why? Scientists believe the answer lies deep within the Moon's core. One leading theory suggests that the Moon's magnetic field was powered by a dynamo effect similar to Earth's. This process requires a molten, electrically conductive core that generates a magnetic field as it moves. Early in its history, the Moon's core was likely molten, possibly due to heat from its formation or the gravitational tug of Earth. However, as the Moon cooled over time, its core began to solidify, shutting down the dynamo and causing the magnetic field to fade away. But there's a twist. Some studies suggest that the Moon's magnetic field didn't just fade gradually, it may have experienced sudden, dramatic changes. For example, lunar rocks collected during the Apollo missions show evidence of brief but intense magnetic activity long after the Moon's core should have cooled. This has led scientists to propose alternative explanations, such as impacts from massive asteroids. These collisions could have temporarily stirred the Moon's core, reigniting the dynamo for short periods before it ultimately died out. The disappearance of the Moon's magnetic field has profound implications for our understanding of lunar history. Without a magnetic shield, the Moon became exposed to the full force of solar radiation and cosmic rays, which likely played a role in shaping its surface and atmosphere, or lack thereof. It also raises questions about how other small, rocky bodies in the solar system, like Mercury or even exoplanets, might have experienced similar magnetic histories. As we continue to study the Moon, each discovery brings us closer to unraveling the story of its magnetic past. And with that, we set our sights on another cosmic mystery, one that challenges our understanding of the universe itself, the mysterious alignment known as the axis of evil. Now shifting our gaze to a cosmic mystery that defies our fundamental understanding of the universe, we encounter the so-called axis of evil. This peculiar phenomenon refers to an unexpected alignment in the cosmic microwave background radiation, the faint afterglow of the Big Bang. What makes this alignment so baffling is that it seems to correlate with the plane of our solar system, a connection that shouldn't exist according to the cosmological principle. The cosmological principle is a cornerstone of modern astronomy, stating that the universe is uniform and looks the same in all directions on a large scale. This principle underpins much of our understanding of the cosmos, from the distribution of galaxies to the behavior of dark energy. However, the axis of evil throws a wrench into this idea. When scientists mapped the cosmic microwave background, they discovered patterns that appeared to align with the orientation of our solar system. This alignment suggests that our local environment might somehow be influencing the structure of the universe on the largest scales, a notion that challenges the very foundation of cosmology. One possible explanation is that this alignment is a statistical fluke, a random coincidence in the data. But the odds of such a coincidence are astronomically low, leading some researchers to question whether there's more to it. Could there be an unknown physical process at work, one that connects the large-scale structure of the universe to our tiny corner of it? Or does this alignment hint at a deeper flaw in our understanding of the Big Bang and the early universe? Another intriguing possibility is that the axis of evil points to the existence of something beyond our current models, such as a pre-Big Bang structure or a hidden dimension influencing the cosmos. While these ideas remain speculative, they highlight how much we still have to learn about the universe. The axis of evil isn't just a curiosity, it's a profound challenge to our understanding of reality itself. As we grapple with this cosmic puzzle, it reminds us that even our most fundamental assumptions about the universe can be called into question. And with that, we turn our attention to another enigma that pushes the boundaries of physics, the black hole information paradox. Now turning to one of the most perplexing puzzles in modern physics, we delve into the black hole information paradox. This mystery sits at the heart of a fundamental conflict between two pillars of science, quantum mechanics and general relativity. At its core, the paradox revolves around a simple yet profound question: what happens to information when it falls into a black hole? According to general relativity, Once something crosses a black hole's event horizon, it's gone forever, lost to the universe. But quantum mechanics tells us that information can never truly be destroyed. So, which is it? This contradiction has left scientists scratching their heads for decades. The paradox gained prominence thanks to the groundbreaking work of Stephen Hawking. In the 1970s, Hawking proposed that black holes aren't completely black. They emit radiation, now known as Hawking radiation. This radiation, he argued, causes black holes to slowly evaporate over time. But here's the catch: if a black hole evaporates completely, what happens to all the information about the matter that fell into it? Hawking initially suggested that the information is irretrievably lost, a conclusion that sent shockwaves through the scientific community. If true, it would mean rewriting the rules of quantum mechanics, which insist that information must always be preserved. This dilemma has sparked a flurry of theories aimed at resolving the paradox. One of the most compelling ideas is the holographic principle, which suggests that all the information swallowed by a black hole isn't lost but is instead encoded on its event horizon, the boundary beyond which nothing can escape. Imagine the event horizon as a cosmic hard drive, storing every bit of data about what falls into the black hole. This theory draws a fascinating parallel between black holes and holograms, where a two-dimensional surface can encode all the information of a three-dimensional object. If true, it would mean that the information isn't destroyed but transformed in a way we don't yet fully understand. Another intriguing proposal is the idea of black hole firewalls. Some physicists argue that instead of a smooth event horizon, black holes might have a fiery boundary that destroys anything crossing it. While this idea resolves the information paradox, it comes with its own set of challenges, as it contradicts the predictions of general relativity. Then there's the concept of black hole remnants, tiny, indestructible leftovers from evaporated black holes that could preserve information. Each of these theories offers a unique perspective, but none have been conclusively proven, leaving the paradox unresolved. The black hole information paradox isn't just an abstract theoretical problem. It has profound implications for our understanding of reality. It forces us to confront the limits of our current theories and pushes us to explore new frontiers in physics. Whether the solution lies in holography, firewalls, or something entirely unexpected, one thing is clear: black holes continue to be one of the universe's greatest enigmas. And as we ponder this cosmic riddle, we're reminded that even the most fundamental laws of nature are still up for debate. With that, we shift our focus to another mystery that challenges our understanding of the cosmos, the Hubble tension. Now shifting our gaze to another cosmic conundrum, we encounter the Hubble tension, a puzzle that has astronomers and cosmologists locked in a heated debate. At its heart, this mystery revolves around a simple yet profound question: how fast is the universe expanding? You might think this is a straightforward question, but the answer depends on how you measure it, and that's where things get complicated. The Hubble tension arises from a discrepancy in the measured value of the Hubble constant, which represents the rate at which the universe is expanding. Scientists use two primary methods to calculate this number. The first method looks at the cosmic microwave background, the faint afterglow of the Big Bang, using data from missions like the Planck satellite. This approach gives us a value for the Hubble constant based on the early universe. The second method relies on observing nearby objects such as Cepheid variable stars and Type 1 a supernova, which act as cosmic yardsticks. These observations provide a measurement of the Hubble constant based on the universe as it is today. Here's the catch: these two methods don't agree. The Planck data suggests a slower expansion rate, while observations of nearby objects indicate a faster one. The difference might seem small, but in the precise world of cosmology, it's a glaring inconsistency. This tension has persisted for years, defying easy explanation and raising questions about our understanding of the universe. So, what could be causing this discrepancy? One possibility is that there's an error in our measurements, though repeated observations have only deepened the mystery. Another idea is that our understanding of the universe's composition might be incomplete. For instance, could there be an unknown form of dark energy or dark matter influencing the expansion rate? Some theorists have even proposed modifications to Einstein's theory of general relativity to account for the tension, though these ideas remain speculative. The implications of the Hubble tension are profound. If it's not resolved, it could mean that our current model of the universe, known as the lambda cold dark matter model, is missing a crucial piece. This model has been remarkably successful in explaining a wide range of cosmic phenomena, but the Hubble tension suggests there might be more to the story. Resolving this mystery could lead to groundbreaking discoveries, reshaping our understanding of the cosmos. As we grapple with this enigma, one thing is clear: the Hubble tension is more than just a technical disagreement, it's a window into the unknown. Whether the solution lies in new physics, better measurements, or something entirely unexpected, this puzzle reminds us that the universe still holds many secrets. And with that, we turn our attention to another cosmic mystery, the missing baryon problem. Now turning to another cosmic mystery, we delve into the missing baryon problem, a puzzle that challenges our understanding of the universe's most basic building blocks. Baryons are the particles that make up the ordinary matter we're familiar with: protons, neutrons, and the atoms that form stars, planets, and even us. Yet when scientists tally up all the baryons predicted by the Big Bang Theory, they find a significant portion is unaccounted for. Where could this missing matter be hiding? The answer might lie in the vast, diffuse regions of space known as the warm-hot intergalactic medium, or WIM for short. This elusive web of gas, heated to millions of degrees, stretches between galaxies and galaxy clusters. While it's incredibly difficult to detect directly, astronomers have used indirect methods such as observing how light from distant quasars is absorbed by this gas to infer its presence. The WIM is thought to contain a substantial fraction of the missing baryons, but confirming this has proven to be a monumental challenge. Another possibility is that the missing baryons are hiding in the form of faint, diffuse clouds of gas within galaxy clusters or even in the outer regions of galaxies themselves. These clouds are so faint and spread out that they evade detection by most telescopes. Some researchers have also suggested that a portion of the missing matter could be tied up in low-mass stars or rogue planets drifting through interstellar space, though these ideas remain speculative. The implications of solving the missing baryon problem are profound. Ordinary matter, though it makes up only a small fraction of the universe's total mass and energy, is crucial for understanding how galaxies form and evolve. If we can locate these missing baryons, it would provide a more complete picture of the universe's structure and history. It could also help refine our models of cosmic evolution, shedding light on how the universe transitioned from a smooth, uniform state after the Big Bang to the intricate web of galaxies and clusters we see today. As we continue to search for these elusive particles, one thing is certain: the missing baryon problem is a reminder that even the most familiar components of the universe can still hold surprises. With each new discovery, we inch closer to solving this cosmic puzzle, bringing us one step closer to understanding the full story of the universe. And with that, we move forward to explore another enigma, the galactic center excess. Now shifting our gaze to the heart of our galaxy, we encounter the galactic center excess, a mysterious glow of gamma-ray radiation emanating from the Milky Way's core. This unexplained phenomenon has puzzled astronomers for years, as the intensity and distribution of this radiation don't align with known sources like stars, gas, or black holes. So, what could be causing this strange excess of energy? One leading theory points to dark matter, the invisible substance that makes up a significant portion of the universe's mass. Some scientists propose that dark matter particles could be colliding and annihilating each other near the galactic center, releasing gamma rays in the process. This idea is tantalizing because it could provide indirect evidence of dark matter, something that has eluded direct detection despite decades of searching. However, the challenge lies in distinguishing this signal from other potential sources of gamma rays. Another possibility is that the excess radiation comes from a population of rapidly spinning neutron stars known as pulsars. These dense stellar remnants emit beams of radiation as they rotate, and if enough of them are clustered near the galactic center, they could collectively produce the observed gamma-ray glow. While this explanation fits some of the data, it doesn't fully account for the excess's specific energy distribution, leaving room for debate. Adding to the intrigue, some researchers have suggested that the galactic center excess could be a combination of both dark matter annihilation and pulsars. This hybrid model attempts to reconcile the strengths and weaknesses of each theory, offering a more nuanced explanation. Yet, without definitive evidence, the true cause remains shrouded in mystery. The implications of solving this puzzle are immense. If dark matter is indeed responsible, it would be a groundbreaking discovery, shedding light on one of the universe's greatest enigmas. On the other hand, if pulsars or another astrophysical source are to blame, it would deepen our understanding of the dynamic processes at work in the galactic core. Either way, the galactic center excess serves as a reminder that even our own galaxy holds secrets waiting to be uncovered. As we continue to probe the mysteries of the Milky Way's heart, the next chapter of our journey takes us to the Eridanus supervoid, a vast emptiness in space that may hold clues to another cosmic puzzle. Now venturing into the depths of the cosmos, we encounter the Eridanus supervoid, one of the largest and most mysterious empty regions in the universe. Spanning an astonishing 330 million light-years, this vast expanse of nothingness challenges our understanding of how the universe is structured. But what makes this supervoid truly fascinating is its potential connection to the cold spot, a puzzling anomaly in the cosmic microwave background radiation, the afterglow of the Big Bang. The cold spot is an unusually cold region in the otherwise uniform cosmic microwave background, and its existence has long baffled scientists. One leading explanation is that the Eridanus supervoid could be responsible. The idea is that as light travels through such a massive void, it loses energy due to the expansion of space, a phenomenon known as the integrated Sachs-Wolfe effect. This energy loss could manifest as a colder region in the cosmic microwave background, aligning with the observed cold spot. However, the sheer size of the supervoid required to produce this effect is so enormous that it pushes the limits of our current cosmological models. This raises intriguing questions about the Big Bang theory itself. If the Eridanus supervoid is indeed the cause of the cold spot, it could imply that the universe's large-scale structure is even more complex and varied than we thought. Some researchers have even speculated that the supervoid might be evidence of a collision with another universe, a concept that ventures into the realm of multiverse theories. While this idea is highly speculative, it underscores how much we still have to learn about the cosmos. On the other hand, not all scientists are convinced that the supervoid fully explains the cold spot. Some argue that the void isn't large enough or dense enough to account for the anomaly, suggesting that other factors such as primordial fluctuations in the early universe might be at play. This ongoing debate highlights the challenges of interpreting cosmic phenomena and the need for more precise observations. The Eridanus supervoid and its potential link to the cold spot remind us that even the emptiest regions of space can hold profound secrets. Whether it's a key to understanding the universe's structure or a clue to entirely new physics, this cosmic void continues to captivate astronomers and cosmologists alike. As we ponder its mysteries, our journey takes us next to the Red Rectangle Nebula, a celestial object whose unique shape and composition defy conventional explanations. Now shifting our gaze to a truly peculiar cosmic wonder, we arrive at the Red Rectangle Nebula, a celestial object that stands out not just for its striking appearance but also for the mysteries it holds. Located about 2,300 light-years away in the constellation Monoceros, this nebula earned its name from its distinct rectangular shape and reddish hue, a feature rarely seen in the cosmos. But what makes the Red Rectangle Nebula so extraordinary isn't just its shape. It's the secrets it reveals about the life and death of stars. At the heart of the Red Rectangle lies a binary star system where two stars orbit each other in a delicate cosmic dance. One of these stars is in the final stages of its life, shedding its outer layers and creating the nebula's intricate structure. What's fascinating is that the expelled material doesn't form the typical spherical or irregular shapes seen in most planetary nebulae. Instead, it takes on a highly symmetrical, almost geometric form, with ladder-like rungs of dust and gas extending outward. This unusual structure has left scientists scratching their heads as it defies conventional models of how such nebulae should evolve. Adding to the mystery is the nebula's chemical composition. The Red Rectangle is rich in complex organic molecules, including hydrocarbons, which are the building blocks of life. These molecules are typically found in the interstellar medium, but their abundance and arrangement in this nebula are unlike anything observed elsewhere. Some researchers speculate that the binary star system's unique dynamics might be responsible for creating these molecules, but the exact process remains unclear. This raises intriguing questions about how such complex chemistry can arise in the harsh environment of space. The Red Rectangle Nebula also challenges our understanding of stellar evolution. Most stars end their lives by expelling their outer layers, forming planetary nebulae that eventually disperse into space. But the Red Rectangle's precise geometric structure suggests that there's more to this process than we currently understand. Could magnetic fields or the interaction between the two stars be shaping the nebula in such a unique way? Or is there some other force at play that we haven't yet discovered? As we continue to study this enigmatic nebula, it serves as a reminder that even the most familiar processes in the universe can hold surprises. The Red Rectangle Nebula not only captivates us with its beauty, but also pushes the boundaries of our knowledge, urging us to rethink what we know about the life cycles of stars. And as we ponder its mysteries, our journey takes us next to the Boötes Void, another cosmic enigma that challenges our understanding of the universe's vast emptiness. Now venturing into one of the most baffling regions of the cosmos, we encounter the Boötes Void, a vast expanse of emptiness that defies our understanding of the universe's structure. Spanning an astonishing 330 million light-years, this void is one of the largest known in the observable universe. To put that into perspective, if you were to place the Milky Way galaxy at one end of the Boötes Void, it would take light traveling at its incredible speed, over 300 million years, to reach the other side. Yet, despite its immense size, this region is almost entirely devoid of galaxies, stars, and even the faintest traces of matter. It's a cosmic desert on a scale that's hard to comprehend. The Boötes Void, named after the constellation in which it lies, was first discovered in the 1980s during surveys of the universe's large-scale structure. Astronomers expected to find a relatively even distribution of galaxies, but instead they stumbled upon this enormous, nearly empty region. The void's existence challenges our understanding of how matter is distributed in the universe. According to the Big Bang theory and the cosmological principle, matter should be spread out more or less uniformly, but the Boötes Void stands as a glaring exception, raising questions about whether our models of the universe's evolution are complete. One of the leading theories about the Boötes Void's formation suggests that it might be the result of smaller voids merging over billions of years. Imagine bubbles in a foam. When they collide and combine, they create larger empty spaces. In the case of the Boötes Void, this process could have led to the creation of a supervoid. However, this explanation doesn't fully account for why the void is so exceptionally empty. Even in regions where voids merge, astronomers would expect to find at least some galaxies or clusters. Yet, the Boötes void contains only a handful of galaxies, making it one of the most desolate places in the universe. Another intriguing possibility is that the Boötes void might be linked to dark energy, the mysterious force driving the accelerated expansion of the universe. Some scientists speculate that dark energy could have played a role in pushing matter away from this region, leaving behind an enormous void. However, this idea is still highly speculative, and there's no direct evidence to support it. The void's emptiness remains a puzzle, and its existence continues to challenge our understanding of cosmic evolution. The Boötes void also raises questions about the nature of the universe itself. Could there be other voids of similar or even greater size lurking in the cosmos, waiting to be discovered? And if so, what do they tell us about the universe's structure and history? These questions highlight the importance of studying such anomalies as they push us to refine our theories and deepen our understanding of the cosmos. As we ponder the mysteries of the Boötes void, we're reminded that the universe is full of surprises, even in its emptiest corners. This vast expanse of nothingness challenges our assumptions and invites us to explore the unknown. And as we continue our journey through the cosmos, our next stop takes us to the rotation curves of galaxies, where another enigma awaits, one that hints at the presence of something invisible yet profoundly influential. Now shifting our gaze to the spinning dance of galaxies, we encounter a mystery that has puzzled astronomers for decades: the rotation curves of galaxies. When scientists first began measuring how fast stars and gas clouds orbit the centers of galaxies, they expected a simple pattern. Based on the visible matter, stars, gas, and dust, they predicted that stars farther from the galactic center would move slower, much like planets in our solar system slow down as they orbit farther from the sun. But what they found was something entirely unexpected. Instead of slowing down, stars and gas at the outer edges of galaxies were moving just as fast as those closer to the center. This discovery defied the laws of gravity as we understood them. According to Newton's and Einstein's theories, the gravitational pull from the visible matter should weaken with distance, causing outer stars to orbit more slowly. But the observations showed no such decline. This discrepancy between prediction and reality became known as the galaxy rotation problem, and it hinted at something invisible at work. To explain this anomaly, astronomers proposed the existence of dark matter, a mysterious substance that doesn't emit, absorb, or reflect light, making it invisible to our telescopes. Dark matter, they suggested, forms a vast halo around galaxies, extending far beyond the visible edges. This halo's gravitational pull would explain why stars on the outskirts of galaxies move so quickly. Even though we can't see dark matter directly, its presence is inferred through its gravitational effects on the visible universe. The dark matter hypothesis has become one of the cornerstones of modern astrophysics, but it raises as many questions as it answers. What is dark matter made of? Is it a single type of particle or a mix of different substances? And how does it interact with the ordinary matter we can see? Despite decades of research, dark matter remains elusive, with experiments around the world still searching for definitive evidence of its existence. The rotation curves of galaxies not only revealed the need for dark matter, but also reshaped our understanding of the universe's composition. Today, scientists estimate that dark matter makes up about 85% of all matter in the cosmos, while the stars, planets, and gas we see account for just a small fraction. This invisible scaffolding holds galaxies together and shapes the large-scale structure of the universe, yet its true nature remains one of the greatest unsolved mysteries in science. As we reflect on the implications of galaxy rotation curves, we're reminded that the universe often hides its secrets in plain sight. What appears to be empty space or a simple spiral of stars may hold clues to forces and substances we've yet to fully understand. And as we continue our exploration, Our next stop takes us to the Sun's outer atmosphere, where another enigma awaits: the mystery of why the solar corona is millions of degrees hotter than the Sun's surface. Now, as we turn our attention to the Sun, we encounter a puzzle that has baffled scientists for decades: the mystery of the solar corona's extreme heat. The Sun's surface, known as the photosphere, burns at a scorching 5,500 degrees Celsius. Yet just above it, in the outer atmosphere called the corona, temperatures skyrocket to millions of degrees. This counterintuitive phenomenon, where the outer layer is far hotter than the surface beneath it, defies our basic understanding of heat and energy. At first glance, it seems logical that the Sun's heat would diminish as you move away from its core. After all, the core is where nuclear fusion occurs, generating the immense energy that powers our star. But the corona's extreme temperatures suggest that something extraordinary is happening in the Sun's outer layers. Scientists have proposed several theories to explain this enigma, with magnetic fields and nanoflares emerging as leading candidates. One prominent theory points to the Sun's complex magnetic fields. The Sun is a dynamic, churning ball of plasma, and its magnetic fields are constantly twisting, breaking, and reconnecting. These magnetic interactions can release enormous amounts of energy, heating the corona to incredible temperatures. Imagine a tangled web of magnetic lines, snapping and reconnecting like elastic bands, each release sending waves of energy rippling through the corona. This process, known as magnetic reconnection, could be a key driver of the corona's heat. Another intriguing possibility involves nanoflares, tiny, frequent bursts of energy that occur across the Sun's surface. While individual nanoflares are too small to observe directly, their cumulative effect could explain the corona's intense heat. Think of it like a campfire. One spark might not produce much warmth, but countless sparks over time can create a roaring blaze. Similarly, millions of nanoflares erupting across the Sun could collectively heat the corona to millions of degrees. Despite these compelling theories, the exact mechanism behind the corona's heat remains elusive. The challenge lies in the Sun's complexity and the difficulty of observing its outer layers in detail. Space missions like NASA's Parker Solar Probe are now venturing closer to the Sun than ever before, gathering data that could shed light on this enduring mystery. Each new discovery brings us closer to understanding how our star works, but the corona's heat continues to remind us that even the Sun, the most familiar object in our sky, holds secrets we have yet to unravel. As we ponder the Sun's hidden dynamics, our journey through the cosmos takes us to another enigmatic event: the Tunguska explosion of 1908, a cataclysmic event that flattened forests and left no crater. What caused this mysterious blast, and why does it still captivate scientists today? Let's find out. Now, shifting our gaze from the Sun's fiery mysteries, we arrive at one of the most dramatic and puzzling events in modern history: the Tunguska explosion of 1908. On the morning of June 30th, a massive blast rocked the remote forests of Siberia, releasing energy equivalent to 10 to 15 million tons of TNT. The explosion flattened an estimated 2,000 square kilometers of forest, snapping trees like matchsticks and sending shockwaves that were detected as far away as Europe. Yet, despite the sheer scale of destruction, no crater was ever found. This absence of a crater has fueled decades of speculation and debate among scientists, making the Tunguska event one of the most enduring astronomical mysteries. The leading theory suggests that the explosion was caused by a comet or asteroid entering Earth's atmosphere. As the object hurtled toward the ground at incredible speeds, the intense heat and pressure caused it to disintegrate and explode several kilometers above the surface. This type of airburst, rather than a ground impact, would explain the widespread devastation without leaving a crater. Imagine a massive fireball erupting in the sky, its shockwave rippling outward and leveling everything in its path. Such an event would have been both awe-inspiring and terrifying for anyone who witnessed it. However, the lack of physical evidence has left room for alternative explanations. Some researchers propose that the explosion could have been caused by a fragment of a comet composed primarily of ice and dust. Unlike a rocky asteroid, a comet fragment might have completely vaporized upon entering the atmosphere, leaving no trace behind. Others have even speculated about more exotic possibilities, such as a small black hole passing through Earth or the release of natural gas from beneath the surface. While these ideas are intriguing, they remain speculative, as no definitive proof has been found to support them. The Tunguska event also highlights the challenges of studying such rare and unpredictable phenomena. The remote location of the explosion, combined with the limited technology of the early 20th century, meant that scientists could not investigate the site thoroughly until decades later. Even today, the exact nature of the object that caused the explosion remains uncertain. Modern simulations and comparisons to other airburst events, like the Chelyabinsk meteor of 2013, have provided valuable insights, but the Tunguska event continues to defy a complete explanation. As we reflect on this extraordinary event, it serves as a stark reminder of the potential dangers posed by near-Earth objects. The Tunguska explosion, though rare, underscores the importance of monitoring our skies and understanding the risks associated with asteroids and comets. With each new discovery, we come closer to unraveling the mysteries of our solar system, but the Tunguska event remains a powerful testament to the unpredictable and awe-inspiring forces at work in the cosmos. Turning now to another celestial mystery, we explore the enigmatic glow known as the zodiacal light, a subtle yet fascinating phenomenon that has puzzled astronomers for centuries. What causes this ethereal light, and what secrets does it hold about the structure of our solar system? Let's dive in. Now, as we shift our focus to the night sky, let's uncover the secrets of the zodiacal light, a subtle yet mesmerizing phenomenon that has captivated stargazers for centuries. This faint triangular glow, often visible just after sunset or before sunrise, stretches upward from the horizon, creating a celestial pathway that seems to guide the stars. But what exactly is this mysterious light, and where does it come from? The zodiacal light is caused by sunlight reflecting off countless tiny particles of cosmic dust scattered throughout the inner solar system. These particles, often no larger than grains of sand, form a vast flattened cloud that extends from the sun outward, following the plane of the solar system. When sunlight hits these particles, it scatters, creating the soft, ethereal glow we see from Earth. Imagine billions of tiny mirrors floating in space, catching the sun's rays and casting a faint, ghostly light across the night sky. Despite its beauty, the origins of this cosmic dust remain a mystery. One leading theory suggests that the dust is the debris left behind by comets as they travel through the solar system. As comets pass close to the sun, they shed ice, dust, and gas, leaving trails of material in their wake. Over time, these trails accumulate, forming the diffuse cloud responsible for the zodiacal light. Another possibility is that the dust comes from collisions between asteroids, which grind rocks into fine particles that spread throughout the solar system. However, not all of the zodiacal light's secrets have been revealed. For instance, scientists have struggled to explain why the dust cloud is so evenly distributed and why it persists over time. You'd expect that the sun's gravity and radiation would gradually clear away this dust, yet it remains a constant presence. Some researchers speculate that there may be a continuous source replenishing the dust, such as ongoing asteroid collisions or the steady disintegration of comets. Others suggest that the dust might be redistributed by forces like solar wind or the gravitational influence of planets. Adding to the mystery, the zodiacal light also holds clues about the structure of our solar system. By studying its brightness and distribution, astronomers can map the density of dust in different regions, revealing patterns that hint at the movements of planets and other celestial bodies. Yet, even with advanced telescopes and space probes, much about this phenomenon remains poorly understood. For example, why does the zodiacal light appear brighter in certain directions? And what role does it play in the broader dynamics of the solar system? The zodiacal light is more than just a beautiful sight. It's a window into the hidden workings of our cosmic neighborhood. As we continue to study this enigmatic glow, we may uncover new insights about the formation and evolution of the solar system. But for now, it remains a gentle reminder of the countless mysteries that still linger in the vast expanse of space. With this celestial glow still fresh in our minds, let's turn our attention to another cosmic puzzle, the search for a hypothetical ninth planet lurking in the outer reaches of our solar system. What evidence points to its existence, and why has it remained so elusive? Let's explore. Now, as we venture deeper into the outer reaches of our solar system, we encounter one of the most tantalizing mysteries in modern astronomy, the search for Planet 9. This hypothetical world, thought to be lurking far beyond Neptune, has sparked both excitement and skepticism among scientists. But what exactly is the evidence for its existence, and why has it remained so elusive? The idea of a ninth planet first gained traction when astronomers noticed peculiar patterns in the orbits of distant objects in the Kuiper belt, a region of icy bodies beyond Neptune. These objects, known as trans-Neptunian objects, seem to cluster in ways that couldn't be explained by the gravitational influence of the known planets alone. Their orbits were tilted and elongated, as if something massive were tugging on them from the shadows. This led researchers to propose that an unseen planet, perhaps 10 times the mass of Earth, could be responsible for these strange alignments. But how could such a large planet remain hidden? The answer lies in its distance. Planet 9, if it exists, is thought to orbit the Sun at a staggering distance, up to 20 times farther than Neptune. At such a vast remove, it would reflect very little sunlight, making it incredibly difficult to detect with current telescopes. To put it in perspective, if you were standing on Planet 9, the Sun would appear as little more than a bright star in the sky. This extreme distance also means that its orbit would take tens of thousands of years to complete, making it a slow-moving target for astronomers to track. The potential effects of Planet 9 extend far beyond the Kuiper belt. Some scientists believe it could explain other anomalies in the solar system, such as the unusual tilt of the Sun's axis or the strange orbits of certain comets. Its gravitational influence might even have played a role in shaping the early solar system, scattering objects into their current positions. Yet, despite these compelling clues, direct evidence of Planet 9 remains frustratingly out of reach. Detecting this distant world is no small feat. Astronomers are using some of the most advanced telescopes on Earth, as well as data from space missions, to scan the skies for any sign of it. The challenge is compounded by the fact that Planet 9's exact location is unknown, requiring researchers to search vast swaths of the night sky. Some have turned to citizen science projects, enlisting the help of amateur astronomers to sift through data in the hopes of spotting this elusive planet. The search for Planet 9 is more than just a quest for a new world. It's a journey to understand the hidden dynamics of our solar system. Whether it's a massive planet, a cluster of smaller objects, or something entirely unexpected, the answer could reshape our understanding of the cosmos. For now, the mystery of Planet 9 remains one of the most intriguing puzzles in astronomy, a reminder that even in our own cosmic backyard, there are still secrets waiting to be uncovered. As we ponder the possibility of this distant world, let's turn our gaze to another cosmic enigma, the mysterious excess of high-energy cosmic rays detected by observatories around the world. What could be producing these powerful particles, and what do they tell us about the universe? Let's explore. Now, shifting our focus to the skies above, we encounter another cosmic mystery that has left scientists scratching their heads: the cosmic ray anomaly. These high-energy particles, traveling at nearly the speed of light, bombard Earth from all directions. But what's puzzling is the unexplained excess of these cosmic rays detected by observatories around the globe. Where do they come from, and why are there so many of them? Cosmic rays are not rays in the traditional sense. They're actually charged particles, mostly protons and atomic nuclei, that zip through space with incredible energy. Some of these particles are so powerful that they can rival the energy produced by the most advanced particle accelerators on Earth. But here's the catch. While we know that cosmic rays originate from violent events in the universe, like supernova or the explosive cores of active galaxies, the sheer number of high-energy cosmic rays we detect doesn't quite add up. There's an excess that current models of astrophysics can't fully explain. One leading theory points to supernova, the spectacular explosions of dying stars, as a primary source. When a star goes supernova, it releases an enormous amount of energy, accelerating particles to near light speeds. These particles then travel through space, eventually reaching Earth. But while supernova can account for some of the cosmic rays we observe, they don't fully explain the overabundance of high-energy particles. This has led scientists to consider other possibilities, including more exotic sources like dark matter. Dark matter, the invisible substance that makes up a significant portion of the universe, has long been a subject of fascination and frustration for researchers. While it doesn't interact with light, it does exert gravitational influence, and some theories suggest that dark matter particles could collide and annihilate each other, producing high-energy cosmic rays as a byproduct. If true, this would not only solve the cosmic ray anomaly, but also provide indirect evidence for the existence of dark matter. However, proving this connection remains a daunting challenge. Another intriguing possibility is that cosmic rays are being accelerated by unknown astrophysical processes. For instance, some scientists speculate that extreme environments, like the regions around supermassive black holes or the shockwaves from merging galaxy clusters, could be generating these particles. These environments are so energetic that they might be capable of producing cosmic rays far beyond what we currently understand. Despite decades of research, the cosmic ray anomaly remains unsolved. Observatories like the Pierre Auger Observatory in Argentina and the High-Altitude Water Cherenkov Observatory in Mexico are working tirelessly to map the origins of these particles. By studying their energy levels and trajectories, scientists hope to pinpoint their sources and unravel this cosmic puzzle. The mystery of cosmic rays is more than just an academic curiosity. It's a window into the most extreme processes in the universe. Whether they come from supernova, dark matter, or something entirely unexpected, these particles hold clues to the fundamental workings of the cosmos. As we continue to probe this enigma, we're reminded that even the tiniest particles can carry the secrets of the universe. With this cosmic puzzle still lingering, let's turn our attention to another baffling alignment in the cosmos, the mysterious arrangement of quasars across billions of light years. What could be causing this strange pattern, and what does it reveal about the structure of the universe? Let's dive in. Now, as we venture deeper into the cosmos, we encounter a phenomenon that defies our expectations of how the universe should behave: the mysterious alignment of quasars. These incredibly bright and distant objects, powered by supermassive black holes at the centers of galaxies, are scattered across the universe. But here's the twist: some quasars, separated by billions of light years, appear to be aligned in ways that shouldn't happen by chance. This strange pattern challenges our understanding of the large-scale structure of the universe and raises questions about the forces that might be at work. Quasars are among the most luminous objects in the universe, shining with the energy of trillions of stars. They are so bright that we can see them from billions of light years away, making them invaluable tools for studying the early universe. But when astronomers began mapping their positions, they noticed something odd. In certain regions of the sky, the rotation axes of quasars, essentially the direction in which their jets of energy are pointed, seem to align with one another over vast distances. This alignment spans scales so enormous that it shouldn't be possible under the standard model of cosmology, which assumes that the universe is isotropic or the same in all directions. This discovery has left scientists puzzled. If the universe is truly random and uniform on large scales, why would quasars billions of light-years apart show any kind of coordinated alignment? One possibility is that there's a flaw in our understanding of the universe's structure. The cosmological principle, which states that the universe is homogeneous and isotropic on large scales, is a cornerstone of modern cosmology. But the quasar alignment suggests that there might be large-scale structures or forces at play that we haven't yet accounted for. Some researchers propose that these alignments could be the result of cosmic strings, hypothetical, one-dimensional defects in the fabric of spacetime left over from the early universe. These strings, if they exist, could create gravitational effects that influence the orientation of quasars over vast distances. Another theory suggests that the alignment might be tied to the influence of dark energy, the mysterious force driving the accelerated expansion of the universe. Dark energy could potentially create subtle anisotropies or directional biases on cosmic scales, leading to the observed alignments. However, these ideas remain speculative, and the quasar alignment continues to challenge our understanding of the universe. To make matters even more intriguing, this phenomenon isn't limited to quasars. Similar alignments have been observed in the orientations of galaxies and even in the cosmic microwave background radiation, the afterglow of the Big Bang. These findings suggest that there might be a deeper, underlying pattern to the universe that we're only beginning to glimpse. The mystery of quasar alignment reminds us that the universe is far more complex and interconnected than we once thought. It challenges us to rethink our assumptions and explore new possibilities about the nature of reality. As we continue to study these enigmatic objects, we may uncover clues not only about the structure of the cosmos but also about the fundamental laws that govern it. With this cosmic puzzle still unresolved, let's turn our attention to another intriguing mystery, the sporadic detection of methane on Mars. What could be causing this gas to appear and disappear, and what does it mean for the possibility of life on the red planet? Let's explore. Now shifting our gaze to the red planet, we encounter a mystery that has puzzled scientists for decades: the sporadic detection of methane in Mars' atmosphere. Methane, a gas often associated with life on Earth, has been detected in small but significant amounts on Mars, appearing and disappearing in ways that defy easy explanation. This inconsistency has sparked intense debate about its origins and what it could mean for the possibility of life on Mars. Methane is a molecule that, on Earth, is primarily produced by living organisms such as microbes or through geological processes like volcanic activity. When it was first detected on Mars by the European Space Agency's Mars Express orbiter in 2004, it raised eyebrows. Subsequent observations by NASA, a Curiosity rover, confirmed its presence, but with a twist. The methane levels fluctuated dramatically, sometimes spiking and then vanishing almost entirely. This erratic behavior makes it incredibly difficult to pinpoint its source. One leading theory is that methane on Mars could be produced by microbial life beneath the planet's surface. On Earth, certain microorganisms known as methanogens thrive in oxygen-free environments and produce methane as a byproduct. If similar microbes exist on Mars, they could be releasing methane into the atmosphere, only for it to be broken down by sunlight or chemical reactions over time. This would explain why the gas appears in bursts rather than being consistently present. However, not all scientists are convinced that life is the answer. Another possibility is that the methane is being produced by geological processes. Mars has a history of volcanic activity, and while its volcanoes are currently dormant, they could still release gases trapped beneath the surface. Additionally, a process called serpentinization, where water interacts with certain minerals in the planet's crust, could also generate methane without the need for life. These geological explanations are compelling, but they don't fully account for the irregular patterns of methane detection. Adding to the mystery is the fact that some observations seem to contradict each other. For example, while Curiosity has detected methane near the surface, the European Space Agency's Trace Gas Orbiter, which monitors the atmosphere from above, has found almost no methane at higher altitudes. This discrepancy suggests that the gas might be rapidly destroyed or absorbed before it can spread, or that it's being released in very localized and short-lived bursts. The inconsistency of methane on Mars has made it one of the most tantalizing and frustrating puzzles in planetary science. It's a phenomenon that could point to the existence of life, but it could also be the result of complex geological processes we don't yet fully understand. Either way, solving this mystery could provide profound insights into the history and potential habitability of Mars. As we continue to explore the Red Planet, future missions like NASA Mars Sample Return Program may help us uncover the truth behind this enigmatic gas. Until then, the methane on Mars remains a captivating reminder of how much we still have to learn about our planetary neighbor. With this mystery still lingering, let's turn our attention to another cosmic enigma: the cannibal galaxies that consume their neighbors. What drives these galactic giants to devour others, and what does it tell us about the evolution of the universe? Let's dive in. Now, as we venture deeper into the cosmos, we encounter a phenomenon that reveals the darker, more violent side of the universe: the cannibal galaxies. These cosmic giants, like the Andromeda Galaxy, are known for their insatiable appetite, consuming smaller neighboring galaxies in a process that shapes the very fabric of the universe. But what drives these galactic predators, and why do some galaxies remain untouched while others fall victim to this cosmic feast? Galactic cannibalism, as it's often called, occurs when a larger galaxy gravitationally pulls in and absorbs a smaller one. This process is not a quick or violent collision, but rather a slow, drawn-out dance that can take billions of years. The gravitational forces at play stretch and distort the smaller galaxy, eventually merging its stars, gas, and dust into the larger one. Over time, the smaller galaxy is completely assimilated, leaving behind only faint traces of its existence, such as streams of stars or distorted structures. One of the most famous examples of this phenomenon is the Andromeda Galaxy, our Milky Way's nearest galactic neighbor. Andromeda has a long history of consuming smaller galaxies, and astronomers have identified several remnants of these past mergers within its structure. In fact, Andromeda is on a collision course with our own Milky Way, and in about 4 billion years, the two galaxies will merge in a spectacular event that will reshape both of them forever. This future merger highlights just how common and significant galactic cannibalism is in the evolution of galaxies. But why do some galaxies become cannibals while others remain untouched? The answer lies in their size, environment, and gravitational influence. Larger galaxies like Andromeda have stronger gravitational pulls, making it easier for them to capture and consume smaller neighbors. Additionally, galaxies located in dense regions of the universe, such as galaxy clusters, are more likely to interact and merge due to their proximity. In contrast, smaller or more isolated galaxies, like the Large Magellanic Cloud, often escape this fate, at least for a time. The process of galactic cannibalism has profound implications for the universe. It drives the growth of galaxies, allowing them to accumulate more stars, gas, and dust, which in turn fuels the formation of new stars and planetary systems. It also plays a key role in shaping the large-scale structure of the universe, creating the intricate web of galaxies and voids we observe today. Without this process, the universe as we know it would look very different. Yet, even as we understand the mechanics of galactic cannibalism, many questions remain. Why do some galaxies resist being consumed even in dense environments? What happens to the supermassive black holes at the centers of merging galaxies? And how do these mergers affect the evolution of life within them? these are just some of the mysteries that continue to intrigue astronomers. As we ponder the fate of galaxies like Andromeda and our own Milky Way, we're reminded of the dynamic and ever-changing nature of the universe. Galactic cannibalism is a testament to the forces that shape the cosmos, revealing a universe that is both beautiful and brutal in its complexity. With this cosmic drama in mind, let's turn our attention to another enigmatic phenomenon, the neutrino anomaly. What secrets do these elusive particles hold, and how do they challenge our understanding of the universe? Let's explore. Now, shifting our gaze to the subatomic realm, we encounter one of the most perplexing mysteries in particle physics, the neutrino anomaly. Neutrinos, often called the ghost particles of the universe, are among the most abundant yet elusive particles in existence. They pass through matter almost undetected, rarely interacting with anything, including the very fabric of our planet. But what makes them truly fascinating is their ability to change identities, or flavors, as they travel through space, a phenomenon that has left scientists scratching their heads and questioning the very foundations of our understanding of physics. Neutrinos come in three known flavors: electron neutrinos, muon neutrinos, and tau neutrinos. What's baffling is that these particles don't stay in one flavor as they move. Instead, they oscillate or switch between these states as they travel. This behavior was first observed in experiments studying neutrinos produced by the Sun, where scientists noticed that fewer electron neutrinos were reaching Earth than expected. The missing neutrinos weren't actually missing, they had simply transformed into other flavors along the way. This discovery, known as neutrino oscillation, was groundbreaking because it revealed that neutrinos have mass, a property that contradicts the original predictions of the Standard Model of particle physics. The Standard Model, which describes the fundamental particles and forces of nature, initially assumed that neutrinos were massless, but the discovery of neutrino oscillations forced physicists to rethink this assumption. If neutrinos can change flavors, they must have mass, albeit an incredibly tiny amount. This revelation has opened up a Pandora's box of questions. Why do neutrinos have mass? What determines their masses? And why are they so much lighter than other particles? These questions challenge the completeness of the Standard Model, hinting at the existence of new physics beyond our current understanding. One of the most intriguing aspects of the neutrino anomaly is its potential connection to the universe's matter-antimatter asymmetry. Neutrinos are unique in that they could be their own antiparticles, a property known as being Majorana particles. If true, this could help explain why the universe is dominated by matter rather than antimatter, a mystery that has puzzled scientists for decades. Experiments like the search for neutrinoless double beta decay aim to uncover whether neutrinos are indeed Majorana particles, which would be a monumental breakthrough in physics. Despite decades of research, neutrinos remain enigmatic. Their tiny masses and weak interactions make them incredibly difficult to study, requiring massive detectors buried deep underground to shield them from cosmic interference. Yet, every new discovery about neutrinos brings us closer to unraveling their secrets and perhaps rewriting the laws of physics as we know them. As we grapple with the mysteries of these ghostly particles, we're reminded of how much we still have to learn about the universe. The neutrino anomaly is a testament to the complexity of the cosmos, challenging our assumptions and pushing the boundaries of human knowledge. With this in mind, let's turn our attention to the final phenomenon on our list, the cosmic web. What is this vast, intricate structure that connects the universe, and how does it shape the cosmos as we know it? Let's explore. Now, as we venture into the final frontier of our cosmic journey, we encounter the grand tapestry of the universe itself, the cosmic web. This vast, intricate structure is the backbone of the cosmos, a network of filaments and voids that stretches across billions of light years, connecting galaxies and shaping the very fabric of space. But what exactly is the cosmic web, and how did it come to be? Let's unravel this cosmic mystery. the cosmic web is the largest known structure in the universe, a sprawling network of dark matter and gas that forms the skeleton upon which galaxies are built. Imagine it as a colossal spider's web, with galaxies clustered along the filaments like dewdrops on a thread. These filaments are the highways of the universe, guiding the flow of matter and energy, while the voids between them are vast, empty regions that seem almost devoid of matter. Together, they create a delicate balance, a cosmic dance that has been unfolding since the dawn of time. But how did this intricate structure form? The story begins with the Big Bang, the explosive birth of the universe. In the early moments, the cosmos was a hot, dense soup of particles, but as it expanded and cooled, tiny fluctuations in density began to emerge. These fluctuations, amplified by gravity, grew over billions of years, pulling matter into dense regions and leaving behind empty voids. Dark matter, the invisible scaffolding of the universe, played a crucial role in this process, guiding the formation of filaments and clusters. Ordinary matter, the stuff we can see, followed this dark matter blueprint, condensing into galaxies and stars along the way. Despite our understanding of its origins, the cosmic web remains a profound mystery. Why does it take this specific filamentary form? What determines the size and distribution of the voids? And how does dark matter, which we cannot directly observe, influence the structure so precisely? These questions challenge our understanding of the universe's evolution and the forces that govern it. One of the most puzzling aspects of the cosmic web is its sheer scale and complexity. Mapping it requires observing the distribution of galaxies across vast distances, a task that has only become possible with modern telescopes and advanced simulations. Even then, we've only scratched the surface. The web's intricate details, such as the fine filaments connecting galaxy clusters, remain elusive, hidden in the faint glow of distant gas clouds. The cosmic web also holds clues to some of the universe's deepest mysteries. For instance, it may help us understand the nature of dark energy, the mysterious force driving the accelerated expansion of the universe. By studying how the web evolves over time, scientists hope to uncover the interplay between dark energy, dark matter, and the visible universe. As we stand on the precipice of discovery, the cosmic web reminds us of the universe's boundless complexity. It is a testament to the power of gravity, the persistence of matter, and the enduring mysteries that await us in the cosmos. And with that, we conclude our exploration of the top 30 astronomical phenomena still unexplained by science. Each of these mysteries invites us to look deeper, question further, and marvel at the wonders of the universe. If you've enjoyed this journey through the cosmos, don't forget to like, subscribe, and hit the notification bell for more space mysteries. Until next time, keep looking up. The universe is full of surprises. As we bring our cosmic journey to a close, it's impossible not to marvel at the sheer scale of the mysteries that still surround us. From the enigmatic wow signal to the vast, intricate cosmic web, each of these 30 unexplained phenomena serves as a humbling reminder of how much we have yet to discover. They challenge our understanding, push the boundaries of science, and ignite our curiosity about the universe's deepest secrets. These mysteries are not just gaps in our knowledge, they are invitations to explore, to question, and to dream. They remind us that the universe is far more complex and wondrous than we can currently comprehend. And while we may not have all the answers yet, the pursuit of these questions is what drives science forward, inspiring generations to look up at the stars and wonder. If you've enjoyed this journey through the cosmos, don't forget to share your thoughts in the comments below. What mystery fascinates you the most? Let's keep the conversation going. And if you want to dive deeper into the wonders of space, make sure to hit that like button, subscribe, and ring the notification bell so you never miss an update. Until next time, keep your eyes on the skies. The universe is full of surprises waiting to be uncovered.